Module 1, Lecture B, Array Fundamentals. By the end of this lecture, you will be able to create NumPy ndarrays using constructors, array creation routines, and conversions from Python sequences. Inspect and interpret key ndarray attributes such as shape, nen, size, dtype, and strides. And choose appropriate dtypes for numerical data and understand basic casting behavior in NumPy 2.2.6. NumPy array creation. Arrays from Python lists. Python lists are a natural starting point for working with arrays, but converting them to NumPy arrays gives you major performance and numerical advantages. A NumPy array stores data in a compact, efficient memory block where all elements share the same data type, unlike the more flexible but slower Python list. This uniform structure lets NumPy perform fast, vectorized operations on entire collections of values at once, while still preserving the original order and layout of the data. When converting Python lists to NumPy arrays, you need to think about the shape and number of dimensions you want. A single list becomes a one-dimensional array, while a list of lists becomes a two-dimensional array, where each inner list is treated as a row. NumPy interprets the outer list as the first dimension and the inner lists as the second, as long as those inner lists are compatible in length. This idea extends to higher dimensions. So nested lists can represent more complex data structures as long as they can be arranged into a consistent rectangular block in memory. When you convert a Python list to a NumPy array, the array must use a single data type, so the types of the list elements determine what the array becomes. A list of only integers produces an integer array, while any floating point values lead to a floating point array. If the list mixes types, NumPy chooses a common type, which may convert integers to floats, or, if the elements differ too much, fall back to a general object type. This choice affects later operations. For example, when numeric strings turn into an array of strings that must be converted before doing arithmetic. Knowing the structure and content of your list helps you create arrays that are ready for numerical computation. Python code. Arrays from Python lists. This section shows how to create NumPy arrays from basic Python lists, starting with simple one-dimensional lists, and then moving to two-dimensional lists that become matrix-like arrays. It explains that when you convert these lists, NumPy infers the array's shape from the list structure. The material also highlights that if a list mixes different data types, such as numbers and strings, NumPy chooses a common data type that can represent all the elements, which may change how the data is stored and used. We begin by importing the NumPy library, which is a key tool for working with arrays in Python. NumPy provides a powerful array structure and many functions that let us process these arrays efficiently. By using it, we can perform numerical computations in a structured, optimized way, which is essential for handling data effectively. We begin by creating a simple Python list that holds several integer values, each representing a temperature measured in degrees Fahrenheit. After defining this list, we print it to the console so we can view all the original temperature values. This gives us a clear starting point before performing any additional operations or transformations on the data. We begin by turning a Python list of temperature values into a one-dimensional NumPy array so we can take advantage of NumPy's fast and efficient array operations. After performing this conversion, we display the resulting NumPy array to confirm that the transformation worked correctly and to quickly inspect the stored values. We begin by creating a list of lists, where each inner list represents a row of sales data with dollar amounts, giving us a simple table-like structure for organizing the information. This nested list format makes the sales data easier to manage and analyze. We then print the entire structure to the console to clearly see the original data before any changes are made. Checking this initial output helps confirm that the data is correct and in the expected format before performing any further processing or conversion. We begin by converting a nested list that represents a sales table into a two-dimensional NumPy array, so we can use NumPy's efficient array operations on the data. Once the conversion is done, we print the array to check its structure and values. This verification step helps confirm that the data was transformed correctly and is ready for further analysis or processing. We create a list that contains both whole numbers and decimal numbers to show that Python lists can store mixed data types. After creating this list, we display its contents so you can clearly see the combination of integers and floats. This simple example highlights Python's flexibility in handling different numeric types within a single list. When we convert a list that mixes integers and decimal numbers into a NumPy array, NumPy automatically changes all the values to a common data type that can represent them, which in this case is a float. We can then print the array and its data type to see this result. This behavior shows that NumPy resolves mixed data types by promoting them to a single, consistent type within the array. This script shows how Python lists can be converted into NumPy arrays and how their data types are handled. It first turns a simple list of integer temperatures into a one-dimensional NumPy array that keeps the integer type. It then converts a list of lists representing a sales table into a two-dimensional NumPy array that preserves float values. Finally, it converts a mixed list of integers and floats, where NumPy automatically promotes all values to floats. Overall, the script highlights how NumPy creates arrays from lists and manages data types during these conversions. Constant value arrays. NumPy lets you quickly create arrays filled with a single constant value by specifying only the shape and the number you want. This is useful for setting initial conditions or placeholders, such as starting an image grid with zeros or beginning an algorithm with ones. Using these tools avoids repetitive code, reduces the chance of mistakes, and relies on fast, compiled operations instead of slower Python loops. As a result, you streamline your workflow and get efficient, consistent array allocation. Constant value arrays are simple but powerful tools in numerical work. In data analysis, you might use an array of zeros to track totals or a fixed baseline to compare experimental results. In image processing, they can act as uniform backgrounds or starting masks, and in simulations, they can represent fields with uniform temperature or pressure. The key benefit is that you specify the shape and constant value once, and NumPy efficiently creates a ready-to-use array, which streamlines later computations and workflows. When creating constant value arrays, you should choose the array's shape and data type at the start, because this defines the structure of your data before any changes are made. You might use a one-dimensional array for simple values, or a multi-dimensional array for more complex data. And you must decide whether the numbers should be integers or floating point values. After creation, these arrays can be manipulated like any others and used as flexible building blocks in larger workflows. By mastering these creation routines, you can set up computational tasks efficiently with clear, predictable starting conditions. Python code, constant value arrays. This section shows how to quickly create constant value arrays in NumPy. You will learn how to make arrays filled with zeros, arrays filled with ones, and arrays filled with any custom value you choose. It also highlights how to control the shape and data type of these arrays. Finally, it briefly covers how beginners can make simple updates to these constant arrays once they are created. We begin by importing the NumPy library so we can efficiently create and work with arrays in Python. This import gives us access to NumPy's powerful tools for handling arrays throughout the script. With it, we can easily build arrays filled with zeros or ones and define arrays with specific values as needed. We can use NumPy to quickly create arrays filled with specific values. For example, we can make a 3x4 grid of zeros with floating point values to serve as a default starting state. We can also create a single row of 5 ones with integer values, which is useful for things like counters. Finally, we can build a 2x3 array where every entry is the value 72 as a float, which can represent a constant setting such as a fixed temperature. The code is set up to display information about a grid that is filled entirely with zeros. It first prints a short message explaining that it will show the grid's shape and values. Then it prints the actual grid so you can clearly see its structure and the zero values it contains. The code is set up to display information about a row of ones. It first prints a short message to tell the user that it will show the shape and values of this row. Then it outputs the actual array, which is a single row filled with integer ones, so the user can quickly see what the data looks like. We begin by stating that we are about to show the initial room temperatures measured in Fahrenheit, which sets the context for the output that follows. Then we display the array containing these fixed temperature values so we can clearly see the starting state of the data. This allows us to inspect the original temperatures before making any changes or updates. We update a single value in the temperature array by setting the temperature at the first row and second column to 75 degrees Fahrenheit, representing a room becoming warmer. After making this change, we print a message to indicate that the room temperatures have been updated. We then display the entire temperature array again, so we can see how this one change affects the overall set of temperatures. This script shows how to create and work with constant value arrays using NumPy. It builds a grid of zeros as floating point numbers, a row of ones as integers, and a small array filled with the value 72 to represent room temperatures in Fahrenheit. The arrays are printed so you can see their shapes and initial values. One temperature is then changed from 72 to 75 to simulate a warmer room, and the updated array is printed. Overall, it demonstrates how to create inspect, and modify NumPy arrays efficiently. Range and spaced arrays. Range and spaced arrays let you generate sequences of numbers efficiently without listing each value by hand. With NumPy, you can specify a start, stop, and step, or request a fixed number of points, and it will build an array that fits those settings. This is especially useful for simulating data at regular intervals or sampling functions evenly. Using these tools makes your code shorter, clearer, and less error-prone. NumPy offers two main ways to create arrays. You can define a start value, a stop value, and a fixed step size, which is useful when you want elements at regular intervals. Alternatively, you can define a start value, a stop value, and the total number of points, and NumPy will space them evenly across that range. This second approach is especially helpful in scientific work, such as sampling signals or evaluating models. In both methods, you describe the structure of the sequence, and NumPy automatically builds an array that matches it. When creating range or spaced arrays, it is important to know whether the method you use includes the endpoint or stops just before it, since this affects how you write loops or represent closed intervals, like physical measurements. When the spacing between values is not an exact integer, these arrays rely on floating point numbers, which can introduce tiny rounding errors. In most practical tasks, such as plotting data or building grids, these small inaccuracies do not matter. By choosing the appropriate range strategy and keeping these floating point behaviors in mind, you can build arrays that match your goals and support efficient computation in NumPy. Python code, range and spaced arrays. This section demonstrates how to create numeric ranges in NumPy using two main tools. First, it shows how to build arrays with a specified step size using the function that generates values by step. Then it introduces the function that creates evenly spaced arrays by specifying how many points you want between a start and end value. Finally, it compares how these two approaches handle whether the endpoint is included and how floating point spacing differs, helping you understand their behavior visually and conceptually. In this script, we use the NumPy library, a key tool in Python for efficient numerical computing. NumPy lets us work with arrays and many mathematical functions, which makes handling numerical data much easier. Here, we focus on using NumPy to create arrays that represent ranges and evenly spaced values. This allows us to explore different ways of generating sequences of numbers for numerical work. We use a numerical computing library to create an array of minute values using a function that generates numbers starting at 0 and increasing by 15, stopping before 61. This produces the values 0, 15, 30, 45, and 60. We then print this array with a label indicating that it shows minutes with a step size of 15, making the time intervals clear. We use the linspace function from NumPy to create evenly spaced positions along a 3-foot board. We tell it to start at 0, end at 3, and produce 5 values. This generates 5 positions that include both ends of the board. We then print the resulting array to see these positions along the board. This example shows that the NumPy arange function does not include its stop value in the resulting array. We look at the last value stored in the minutes array which was created with arange, to see the highest minute actually included. Then, we compare it to the stop value used when calling arange, which is 61, and note that this value does not appear in the array. Together, these steps illustrate that arange always excludes the stop endpoint. This example shows that the NumPy linspace function includes both the starting and ending points of arange. By printing the first and last values in the positions array, we see they match the start and end of a 3-foot board. This confirms that linspace includes the 0-foot mark and the 3-foot mark exactly. In other words, it creates evenly spaced values that always contain both boundary points of the interval. We determine the spacing between consecutive positions on the board by subtracting the first position from the second position in the array. This difference represents the distance between each evenly spaced point. We then output this spacing value to confirm that the points are uniformly distributed along the board. This script shows how NumPy can create arrays with specific spacing and how different functions handle endpoints. It first builds an array of minutes from 0 to 60 in steps of 15, illustrating that the final stop value is not included. It then creates an array of positions evenly spaced along a 3-foot board, this time including both the starting and ending points. By comparing these two approaches, the script highlights their different endpoint behavior and finally computes the distance between each pair of neighboring positions on the board to show the consistent spacing in the evenly spaced array. Understanding array attributes. Array shape and dimensions. The shape of an array tells you how many elements it has along each axis and acts like a compact description of its structure. A one-dimensional array is like a simple list, while a two-dimensional array is like a grid with rows and columns. In 3 dimensions, the shape can describe stacks of such grids, for example, a collection of grayscale images. Understanding this structural description is essential, because most numerical computing operations depend on how data is arranged across these dimensions. An array's rank, or number of dimensions, tells you how many indices you need to access an element. A one-dimensional array uses a single index, like selecting a specific day in a time series. A two-dimensional array needs 2 indices, such as choosing a particular patient and their lab result. A 3-dimensional array might use latitude, longitude, and altitude to locate a point in a weather model. As the number of dimensions increases, it becomes essential to keep track of what each axis represents to avoid mixing up concepts like time, space, or different data channels. The shape and dimensions of an array determine how it behaves in operations such as addition, concatenation, and reshaping. For example, exam scores stored in 2 dimensions can be extended to 3 dimensions by adding a semester axis, which changes how the data is grouped without changing the values themselves. Being able to understand and mentally picture an array's structure is essential for more advanced tasks like broadcasting and preparing data as input to models. This understanding makes these processes more intuitive and helps reduce mistakes. Python code, array shape and dimensions. We will use simple NumPy examples to show how array shapes and dimensions work. By starting with small arrays, you can clearly see how the number of rows and columns defines the shape. Then, By adding more axes, you can observe how the shape changes as we move from one-dimensional to two-dimensional and then to three-dimensional arrays. This helps you visualize rows, columns, and layers, and understand how higher dimensional arrays are structured. In this lesson, we use the NumPy library, a key tool for numerical computing in Python. NumPy lets us work efficiently with a large, multidimensional arrays and matrices, and provides many mathematical functions to operate on them. In our script, we rely on NumPy to create and manipulate arrays of different dimensions so we can better understand how array shapes and dimensions behave. We create a one-dimensional NumPy array to store daily temperatures in Fahrenheit, using the values 68, 70, 72, and 71. We then print the array and its shape. The shape tells us that this array has a single dimension with 4 elements, one for each day's temperature. We use a numerical computing library to create a two-dimensional array that stores temperature values for different days and cities. The array is built from 2 inner lists, each holding 2 temperature values. You can think of the first list as temperatures for 2 cities on one day, and the second list as temperatures for the next day. When we print the array and its shape, the shape tells us it has 2 rows and 2 columns, confirming that it is a two-dimensional structure. We build a 3-dimensional array with a numerical library to store data across days, cities, and morning and evening readings. It has 2 layers, each with 2 rows and 2 columns. You can think of the first layer as the first day, holding temperatures for 2 cities, with morning and evening values, and the second layer as the second day. When we check the array's shape, it reports 2 by 2 by 2, confirming there are 2 layers, each containing a 2 by 2 grid of values. We use the ndim attribute to find how many dimensions an array has. A one-dimensional array of temperatures in Fahrenheit has a single dimension. A two-dimensional array of temperatures organized by days and cities has 2 dimensions. A 3-dimensional array that adds morning and evening readings across days and cities has 3 dimensions. Knowing the number of dimensions helps us understand the structure and complexity of each array. We take a one-dimensional array of temperatures and convert it into a 2 by 2 array using the reshape method from the NumPy library. This method changes how the data is organized without modifying the actual values. After reshaping, we display the new array and its shape to confirm the transformation. This process shows how the same data can be restructured to support different types of analysis or visualization. This script uses NumPy arrays to show how shapes and dimensions work. It begins with a one-dimensional array of daily temperatures, then moves to a two-dimensional array for temperatures across days and cities, and then to a three-dimensional array that adds morning and evening readings. It uses the attribute that reports the number of dimensions to make these differences clear. Finally, it reshapes the original one-dimensional array into a 2 by 2 matrix to show that you can change the array's structure while keeping the same data. Overall, the exercise illustrates how organizing data in different dimensions and shapes is important for working with complex scientific datasets. Data types and item size. When working with arrays, The data type, or dtype, is important because it defines what kind of values the array can store, such as integers or floating point numbers. This choice affects how much memory the array uses and what operations are valid. For example, small whole numbers might use a compact integer type, while precise measurements need a floating point type. Understanding the dtype helps you read the array correctly and predict how it will behave in calculations. The item size attribute tells you how many bytes each element in an array uses, which is important for managing memory efficiently. For example, image data can often use a 1 byte per pixel integer type to keep memory usage low, while high-precision financial data may need a larger floating point type to reduce rounding errors. By checking item size, you can estimate the total memory an array will use, which is especially important for large datasets such as climate simulations or sensor networks. Choosing an appropriate data type and item size helps prevent unnecessary memory strain and performance problems. When arrays interact with each other or with external data, their data type and item size control how values are read and stored. Loading data from files or databases often requires matching or converting these formats to NumPy's internal representation. When arrays with different data types are combined, one may be promoted to a larger type, which can increase memory usage, such as when small integers are added to large floating point numbers. Understanding how and when these changes happen helps you balance numerical precision with performance and choose efficient data types for your computations. Python code, data types, and item size. This lesson explains how NumPy array data types and item size work, focusing on how they affect memory usage. You will see how arrays that store integers and arrays that store floating point numbers can hold similar values but use different amounts of memory because each data type has its own item size. By comparing these arrays, you learn that changing the data type can increase or decrease the number of bytes used per element. This change in item size directly affects the total memory required for the entire array, which is important when working with large datasets. We begin by importing the NumPy library, which is essential for working efficiently with numerical arrays and their data types. NumPy lets us handle large collections of numbers in a structured way and perform operations on whole arrays without writing manual loops. In this script, we use NumPy to investigate how choosing different data types for array elements changes the amount of memory those arrays use. We create two NumPy arrays with different data types to compare their memory usage. The first is an integer array using the int8 type, where each element uses 1 byte, making it efficient for small whole numbers. The second is a floating point array using the float64 type, where each element uses 8 bytes and provides higher precision. By contrasting these arrays, we can see how the choice of data type affects both memory consumption and numerical precision. We start by displaying the values in the integer array so we know exactly what data it contains. Then we identify the array's data type to understand how these values are represented in memory. Finally, we report the size in bytes of each element, which tells us the memory cost of storing each integer in the array. We first display the values in the float array so we can see the data we are working with. Then we print the array's data type to understand how these numbers are stored in memory. Finally, we show the size in bytes of each element, which tells us how much memory each float value uses. Together, these steps help us understand the memory implications of choosing this data type. To find the total memory used by an integer array, multiply the number of elements by the size of each integer in bytes. You do the same for a float array by multiplying its number of elements by the size of each float in bytes. These simple calculations show how much memory each array uses and illustrate how different data types lead to different memory consumption. We find the total memory used by an integer array by multiplying how many elements it has by the number of bytes each integer takes. We do the same calculation for a float array. Comparing these totals shows how the choice of data type affects memory usage. In practice, float arrays usually consume more memory than integer arrays. This script shows how the choice of data type in NumPy affects memory usage. It builds one array of small integers using an 8-bit integer type and another array of larger numbers using a 64-bit floating point type. When you inspect them, the integer array has a much smaller item size than the float array, even though both arrays contain the same number of elements. As a result, the total memory used by the integer array is significantly lower. This demonstrates that selecting appropriate data types is important for memory-efficient NumPy arrays. Strides and memory layout. When working with NumPy arrays, it is important to understand not only their shape, but also how their elements are laid out in memory, which is described by strides. Strides tell you how many bytes NumPy moves in memory to reach the next element along each axis. In a two-dimensional array, such as a grayscale image, one stride gives the byte distance between rows, and another gives the distance between neighboring pixels in a row. Although you index arrays using row and column positions, NumPy converts these indices into byte offsets using the strides, which explains how the array is actually stored and accessed in memory. Array strides describe how data is laid out in memory based on the array's shape and data type, and they determine whether the array is stored contiguously or in a more complex pattern. In typical row major storage, elements along the last axis are stored next to each other, so the stride for that axis equals the byte size of one element, while the stride for the first axis equals the size of an entire row. When you slice or transpose an array, NumPy may create a new view with different strides, which can even be negative to represent reversed order. Understanding strides helps you see how array elements are arranged and accessed in memory. Understanding strides and memory layout is important for both performance and correctness. When you access data in memory order, you take advantage of the processor and cache, which makes operations faster, while random access can slow them down. In data analysis, matching your iteration pattern to the strides can turn slow, batch-style work into something that feels interactive. Strides also matter for working with other libraries or languages that expect specific memory layouts. Finally, knowing how shape, data type, and strides interact helps you avoid subtle bugs when operations share underlying data instead of creating separate copies. Python code, strides, and memory layout. This section introduces the basics of how NumPy stores arrays in memory by looking at shape, data type, and strides together. It explains that these three properties determine how elements are laid out and accessed in memory. You compare the stride patterns of a normal, contiguous array with those of a sliced array and a transposed array. to see how different views of the same data change how NumPy steps through memory. The goal is to build an intuitive understanding of how these stride patterns affect performance and behavior when working with arrays. We begin by importing the NumPy library, a standard tool in Python for numerical work. NumPy supports efficient arrays and matrices and offers many mathematical functions that operate on them. In this script, it is crucial because we use these array features to explore how data is stored in memory and how strides work. Understanding NumPy is therefore key to understanding the array memory layout concepts demonstrated here. We create a two-dimensional array by using a function from NumPy that generates numbers from 0 to 11, then reshape the sequence into a 3x4 grid. This grid represents temperature values measured in degrees Fahrenheit. We also specify that each value in the array uses a 64-bit floating point data type, so the numbers are stored with double precision. We begin by printing key information about the array, focusing on its shape, data type, and strides to understand how it is laid out in memory. The shape shows the array's dimensions. The data type tells us what kind of elements it stores, and the strides indicate how many bytes we move in memory to reach the next element along each dimension. Together, these properties reveal how the array is organized and help us predict how operations, especially slicing and transposing, will behave. In this example, we take a slice of the original array that keeps all rows, but only every second column by using a step of 2 along the column dimension. This slice does not create a new copy in memory. Instead, it shares the same underlying data as the original array. The operation changes how the array is stepped through in memory, known as its strides, while the data type of the elements stays the same. We examine a column slice created by taking every second column from the original array and print its shape, data type, and strides. The shape shows that the number of columns has been reduced, but the data type stays the same as float 64. The strides change, revealing how the slice steps through memory and skips elements to select the desired columns. Even though the strides differ, the slice still shares the same underlying data as the original array. We create a transposed view of an array by swapping its rows and columns using the transpose method, which rearranges the array's axes. This does not make a new copy in memory, but instead gives a different way to look at the same data. The main effect is that we can now access the elements in row major order instead of the original column major order. This is efficient because only the access pattern changes, not the underlying data. When we transpose an array, we swap its rows and columns, creating a new view that changes how the data is accessed in memory. The shape of the array updates to show this swap, with the original number of columns now appearing as rows and the original rows as columns. The data type stays the same because transposing does not change the kind of value stored. However, the strides change, reflecting a new pattern for stepping through memory to reach each element, which is a key property of a transposed view. We create a reversed view of the original array by slicing it along the first axis with a negative step, which flips the order of the rows. This uses a negative stride, meaning the data is accessed in reverse along that axis. Importantly, this operation does not make a new copy of the data. It only provides a different view of the same underlying memory. We examine the shape, data type, and strides of a reversed array view. This view flips the order of the rows from the original array. As a result, the stride along the first axis becomes negative. A negative stride means the array's memory is read in reverse for that dimension, which is what causes the rows to be reversed. This script shows how NumPy uses strides to control how array data is laid out and accessed in memory. It begins with a two-dimensional floating point array and prints its shape, data type, and strides, which describe how many bytes you move in memory to step along each dimension. It then creates a slice that skips every second column, a transpose that swaps rows and columns, and a reversed version along the first axis. And in each case, the strides change to match the new access pattern. These operations all create views that share the same underlying data, illustrating how NumPy can efficiently rearrange and access arrays without copying them by adjusting only the stride information. Numeric dtypes and casting. Core numeric dtypes. When working with numerical arrays in NumPy, choosing the right numeric data type is important for accuracy and efficiency. The main data type families are integers, floating point numbers, and complex numbers. Integers store whole numbers and come in different sizes that determine the range of values they can hold. Floating point types represent real numbers with fractional parts, typically using single or double precision, with double precision often used for higher accuracy. Complex types store both real and imaginary parts and are important in areas like signal processing and quantum mechanics. Understanding these options helps you balance precision, memory use, and performance. In NumPy, choosing between signed and unsigned integers depends on whether your data can be negative. Signed integers can represent both positive and negative values, which is useful for data like financial records. Unsigned integers only represent 0 and positive values, but for the same bit size, they can store larger maximum values, making them suitable for things like pixel values or inventory counts. Smaller integer types save memory and can improve performance on large datasets, but they increase the risk of overflow if values exceed their allowed range. To avoid incorrect results, you should match the integer type to the realistic limits of your data. When choosing floating point or complex data types, you are trading off precision against memory and speed. Single precision floats use less memory and are fast, so they work well when exact values are not critical. Double precision floats provide higher accuracy, which is important in simulations or financial models where small rounding errors can accumulate. Complex types store real and imaginary parts as two floats and are useful in areas like signal processing. Overall, you must decide how much rounding error is acceptable and how much memory you can allocate to protect your data's integrity. Python code, core numeric dtypes. In this section, you will use simple NumPy arrays to explore the core numeric data types. You will place integer, floating point, and complex numbers side by side so you can directly compare how each type represents values. You will also clearly examine the difference between signed and unsigned integers by looking at the ranges of values each one can store. Together, these comparisons give you a concise overview of how NumPy handles different kinds of numeric data. We begin by importing the NumPy library, which is a core tool in Python for working with arrays and performing fast numerical calculations. NumPy allows us to create arrays and efficiently manipulate them, which is essential for many scientific and data processing tasks. In this script, our main focus is on using NumPy to handle arrays with different data types. Importing this library is therefore the first step in enabling all the array operations we need. We create several small NumPy arrays to illustrate different numeric data types. First, we make an array of 16-bit signed integers, which can store both positive and negative values. Then we create a 16-bit unsigned integer array, which can only hold non-negative values. Next, we define a 32-bit floating point array for decimal numbers. Finally, we build a 64-bit complex number array to represent values with both real and imaginary parts, showing how each data type serves a specific purpose. The code prints each numeric array along with its data type so you can compare different numeric families. It first shows the signed integer array and labels its type as signed integer 16. Then it displays the unsigned integer array with type unsigned integer 16. After that, it presents the floating point array with type float 32. Finally, it shows the complex number array with type complex 64. Seeing the values and their types side by side highlights how each numeric type is stored and represented. We compare memory usage across several array data types to see how efficient they are. Signed and unsigned integer arrays each use 2 bytes per element, which matches a typical 16-bit integer size. Float arrays use 4 bytes per element, consistent with 32-bit floating point numbers. Complex number arrays use 8 bytes per element because they store both real and imaginary parts as separate 32-bit floats. This comparison shows how choosing different data types directly affects memory usage and performance in data-intensive applications. To show how overflow can occur with small unsigned integers, we create a NumPy array that stores the number 70,000 using an unsigned 16-bit integer type. This type can only represent values up to 65,535. Because 70,000 is larger than this limit, the value wraps around when stored, producing an incorrect result. We then print the stored value to clearly demonstrate this overflow effect. This script shows how different numeric data types work in NumPy arrays, including signed and unsigned integers, floating point numbers, and complex numbers. It prints arrays along with their data types and explains that signed integers can represent both positive and negative values, while unsigned integers can only represent non-negative values. The script compares memory usage per element, noting that signed and unsigned integers use 2 bytes, floats use 4 bytes, and complex numbers use 8 bytes. It also demonstrates overflow by storing a very large value in an unsigned integer, which causes the number to wrap around because of the limited range of that data type. Automatic type promotion. Automatic type promotion in NumPy is the process of choosing a common data type when you combine values or arrays with different types. NumPy selects a result type that can represent all inputs without losing information, following a hierarchy based on range and precision. For example, when you mix integers and floating point numbers, the result becomes a floating point type because it can represent fractions that integers cannot. This means operations that start with integers may produce floating point results. So understanding type promotion helps you predict the data types you will get. NumPy automatically promotes mixed numeric types to a common type that can represent all the values without losing information. When you combine integers with floating point numbers, the result becomes a floating point type, and when you mix real and complex numbers, the result becomes complex. This behavior ensures that all numerical data is preserved, such as when combining low-precision sensor readings with high-precision calibration values. These promotion rules help keep data types consistent, which is important for accurate analysis. When NumPy automatically promotes data types, it can affect performance, memory use, and numerical behavior. Switching to larger or more complex types, such as moving from 32-bit to 64-bit floats, uses more memory and can slow computations, which matters for large datasets. These promotions can also change numerical results by introducing rounding or special values like infinity. By understanding how promotions work and choosing compatible data types in advance, you can either gain precision when needed or avoid unwanted overhead and maintain better control over your calculations. Python code. Automatic type promotion. NumPy automatically promotes data types when you mix different kinds of numbers in the same operation. For example, when integers are combined with floats, the result becomes a float. And when either of those is combined with complex numbers, the result becomes complex. This promotion ensures that no information is lost, such as decimal parts or imaginary components, but it also means the result type may be different from the original inputs. Understanding how result types change helps you predict the output of mixed type calculations and avoid unexpected behavior in numerical code. We begin by importing the NumPy library, which is a key tool in Python for working with arrays and doing fast numerical calculations. This import lets us create arrays with specific data types and apply operations efficiently. It also enables automatic handling of type promotion, so operations between different data types are managed correctly. In short, importing NumPy sets up the numerical foundation for the rest of the script. We use a NumPy array to store daily car counts on a highway, choosing a 16-bit integer type because it efficiently represents small whole numbers. After creating this array, we display its values and its data type to confirm that it was defined correctly. This quick check ensures the data is in the expected format before we perform any further analysis or operations on it. We create an array to store the average weight of cars in pounds using the float 32 data type, which is a single precision floating point format. After creating this array, we print its values and its data type to confirm that the numbers are stored as floats. This setup ensures that later calculations on these car weights use appropriate floating point precision. We multiply an array of integers that represent daily car counts by an array of floating point numbers that represent average car weights. NumPy automatically promotes the result to a floating point array because combining integers with floats requires more precise values. This automatic type promotion helps avoid losing detail in the calculation. After the multiplication, we check and print the data type of the result to confirm that it is a floating point type. Using NumPy, we create a complex number with a real part of 1 and a small imaginary part, and store it in an array with a complex data type. We then multiply this complex value by an existing array of integers. NumPy automatically converts the result to a complex data type so it can represent the imaginary component. Finally, we display the resulting values and their data type to confirm that this promotion to complex numbers has occurred. We create one array of small integers using 16-bit values and another array of larger integers using 64-bit values. When these two arrays are added together, NumPy automatically promotes the result to the larger data type, which is 64-bit integers. This automatic promotion helps avoid overflow that might occur if the smaller type were used. We then check the data type of the result to confirm that this promotion has taken place. This script illustrates how NumPy automatically adjusts data types during calculations to maintain accuracy. When an integer array of car counts is multiplied by a float array of average car weights, NumPy converts the result to floats to preserve precision. When the same integer counts are multiplied by a complex number, the output becomes complex, showing that NumPy can handle complex arithmetic directly. Finally, when small integers are added to very large integers, NumPy promotes the result to a larger integer type to avoid overflow. Together, these examples show how NumPy manages type promotion to prevent data loss in numerical computations. Safe casting choices. When working with numerical arrays, choosing how to cast between data types is a trade-off between safety, precision, and performance. Safe casting means moving to a type that can represent all existing values without overflow or rounding, such as converting a small integer to a larger floating point type. Risky casting, like converting high-precision floats to low-precision integers, can lose fractional information and clip values. In practice, you should select data types that preserve all important values, which is especially critical for sensitive data such as medical dosages or financial transactions. When choosing safe casting between data types, you must be clear about when losing precision is acceptable. In many workflows, it can be reasonable to trade some accuracy for speed or lower memory use, such as storing large volumes of low-quality sensor data in single precision. However, in situations where small changes accumulate, like financial models, moving between low and high precision can introduce significant errors. A good strategy is to perform all critical calculations in high precision and only reduce precision at the final stage when you store or share the results. When working with mixed data types, you need to plan conversions carefully so they happen in a predictable and meaningful way. Automatic type promotion can prevent data loss, but it may convert everything to a less efficient type, such as turning small integers into large floating point numbers. Changing types to save space, like shrinking timestamp integers, can also reduce precision. To ensure safe casting, choose data types that preserve both numerical accuracy and the intended meaning of the data. Document these choices and avoid unnecessary conversions that might introduce errors. Python code, safe casting choices. Demonstrate that converting integers to floating point numbers can be done safely when the float type has enough precision, so no information is lost. In contrast, show that converting precise floating point values to smaller integer types can be unsafe, because values outside the integer range are clipped to the minimum or maximum allowed value. Finally, compare how much memory different numeric types use and emphasize that you should choose data types deliberately, especially for calculations, to balance precision, safety, and memory usage. We begin by using the numerical computing library NumPy in Python, which is designed for fast and efficient work with arrays. This tool is essential for the tasks ahead because it lets us perform mathematical operations quickly and handle large collections of data. In particular, we will rely on it to change data types and to study how much memory different kinds of data use. We create a NumPy array to store daily water usage in gallons, using the values 120, 135, 150, and 160. The array is defined with a 16-bit integer data type. This type is chosen because it provides enough range for typical daily water usage while using memory efficiently. In other words, it balances accuracy and storage needs for this kind of data. We convert the array of daily water usage from integers to a float 64 type so we can perform more precise numerical calculations and analysis. This is done using a NumPy method that changes the data type to floats while creating a new array instead of altering the original one. Converting from integers to floats is safe because it does not lose any information, but it gives us greater flexibility for later computations. We use a float array to store precise fuel amounts in gallons. This array is created with NumPy and given specific values. By choosing a 64-bit floating point data type, we keep high precision and preserve fractional parts. This allows for accurate calculations and analysis of the fuel data. In this step, a float array that stores precise fuel amounts is converted to an 8-bit integer format using a type conversion method from the numerical library. This changes each value to an integer, discarding any fractional part and therefore reducing precision. Because 8-bit integers have a limited range, very large or very small values may also be clipped to the nearest representable value. The conversion is done while creating a separate copy, so the original float array is left unchanged. We first display the data types of the water usage array before and after casting to show that the original integer type is safely converted to a float type, which supports more precise calculations. We then print the array values in both integer and float form. This confirms that converting to floats keeps the same numerical values and does not lose information. Overall, this demonstrates that this casting operation is safe and preserves the original data while enabling higher precision. The code reports that fuel values are being converted from a float data type to an integer data type, specifically from float 64 to int 8. This conversion is labeled unsafe because it removes the fractional part of each float value. The output then shows the values before and after conversion, making it clear that the precise decimal values are truncated to whole numbers. It also highlights that extreme values may be clipped if they fall outside the range that int 8 can represent. This example compares the memory usage of integer and float arrays to show the trade-off between precision and efficiency. An integer array uses fewer bytes, while converting it to floats increases memory use because floats store more precise values. Similarly, a float array originally uses more memory, but converting it to integers reduces the number of bytes at the cost of losing precision. Overall, choosing between integers and floats means balancing how much memory you use against how accurate your data needs to be. This script uses NumPy to show the difference between safe and unsafe typecasting. It first converts an integer array of daily water usage into floats, which keeps all the information while allowing more precise calculations. It then converts a float array of fuel amounts into small integers, which cuts off decimal parts and can clip values, causing a loss of detail. By printing the original and converted arrays and comparing their memory usage, it illustrates that integers use less memory than floats. So you must balance precision against memory efficiency when choosing data types. In this lecture, you learn to create NumPy ndarrays using constructors, array creation routines, and conversions from Python sequences. Inspect and interpret key ndarray attributes such as shape, ndim, size, dtype, and strides. And choose appropriate dtypes for numerical data and understand basic casting behavior in NumPy 2.2.6. In the next lecture, Lecture C, we will go over array operations. Thank you for your attention. See you all in the next lecture.